Today we're going to do the last section in probability and statistics. Recall that in probability we've done multi-event, single-event probability, as well as the counting principles. Within statistics, we've covered central tendency, mean, median, mode, standard deviation, basically the distance around mean, distribution around mean. And finally, we're going to do what is called normal distribution, which is kind of a combination of probability and statistics, but it's most often used as a statistical technique. I'm going to first define what normal distribution is. I think you've heard it more commonly used as the normal curve or the bell curve. But let me first define it. So a normal distribution is a distribution of data that is randomly distributed, hence distribution, about a mean or average. So data is randomly distributed around a mean or average. It is often sometimes called the distribution itself is called a normal curve, or more commonly in common language, the bell curve. Some characteristics of it is continuous, not discrete, which means it's in theory for an infinite number of pieces of data. So you can get a probability for any number. The stuff we've done so far has largely been discrete, both probability and stats. We're doing central tendency, for example. We just had 10 numbers, for example, and you're finding an average. This will be an infinite number of numbers. So that means that you can pick any real number and it'll tell you the probability of something being in there. And as it's used, that probability function is also used for statistics frequently. So what is it used for, or how is it? What is its purpose? Most human characteristics, and actually animal characteristics as well, so biological characteristics, just call it in general, follow normal curves. Characteristics. For example, height, not just of people, but animals, weight, blood pressure, rates, heart rates, IQ, and I'll give a couple of examples in a moment. These all basically have a very similar distributed curve among all humans or all animals. Another common example, this actually shows up in nature, and I'll show you how odd that is in a minute. Why should, for example, weight follow the same characteristic as a heart rate in nature? It's not, and by the way, the same basic structure of the curve for a human as for an ant. That's very strange. It's something built into human nature, or sorry, the natural world. We use those normal curves as well for things that are man-made, like, for example, we put grades typically on bell curves, and the SAT scores are also typically done on bell curves. You'll get very used to these as you go into college. Okay, so that's what a normal curve is. I'm not going to draw one. This is probably the most important thing from this section, so make sure you do a really good drawing. So first of all, a bell curve is distributed around the average. And, not surprisingly, the bell curve looks like a bell. Or normal curve is the actual mathematical term. But you can see how it gets named. Looks like a bell. It's distributed around the average, or mean, so I'm going to put the mean right in the middle there. And then we have standard deviations, just like you would have with any data set, stuff we were doing in the last lesson. You'll go up one standard deviation, that's a sigma for standard deviation, up 2, up 3, etc. Down 1, down 2, and this should be symmetric. Talk about that in a second as well. Down, a little over here, down 3. And there are an infinite number of standard deviations because remember there are an infinite number of data sets across this around the mean. So it goes to 4 standard deviations, 5, 6, 7, 8, 9, 10. When you have a discrete set, eventually you're just going to run out of people over here. And you will run out of people generally here as well. But in theory on the data, you won't. Okay, so there's my distribution. It is symmetric. First of all, a normal distribution is symmetric. And Within the, I'll give you the band rates, between the average and one standard deviation, 34% of the population will exist. And between the mean and one standard deviation below, another 34% will exist. So what that means is that 68% of any data for any of these things, for example, that I put up here, height, weight, blood pressure, etc., 68% of the population will have between one standard deviation of the average or mean of, say, blood pressure. If you go up to 2 standard deviations, there is another, this is just between these two, not the addition, there's another 13.5% between 1 and 2 on both sides. Again, it's symmetric. Now we're up to a total of that's 68, and that is 27. So the total between the first two standard deviations is 95%. So again, one of these characteristics, if you're talking about, say, heart rate, the entire population will be plus or minus 2 standard deviations, 95% of it within the average. The next standard deviation or group up is between 2 and 3. That's 2.35%. And 2.35% over here, again symmetric. That adds another 4.7. So that means between these two here, there's 99.7% of the population is plus or minus 3 standard deviations from the average. And between 2, I'm not going to draw it, I'll draw it up here. It's going to make it a little messy. Between 2, it's 95%. And then between 1, plus or minus 1, it's 68%. There are some tails out here. So notice we're not up to 100%. So if you go plus 3 standard deviations up, you get plus 0.15% for everything above that and 0.15% down here. And that's for 3 to 4 to 5 to 6 to 7 to 8, not each, but in total. So each one of these would have a small number. So I say with it, by the time you got out to 6 standard deviations or so, you'd be at a really tiny percentage, but again, not 0. Okay, so that's your distribution curve. Make sure you have that written down. That's very important. I'm going to use that now for a couple of examples to show you how it works and what its use is. So I'm going to start with height. So hopefully you have that down. I'm going to erase this. And in most of these times you'll calculate a standard deviation, but in this case I'm just going to give you one. So we're going to do height of males in the US. So the average height, the mean, remember is X bar. The average height in America of an average male is 69.5 inches, which is what, 5'9.5" inches. So roughly 5'10". And the standard deviation of the population is 2.5 inches. Okay, so I'm going to draw the bell curve of this with not just so it's theoretical plus or minuses on it, but the actual numbers. Try to make this symmetric as best you can. Okay, so here's my height. This is going to be height. The average is 69.5 inches. The mean is in the middle. Then one standard deviation is 2.5. So I'm going to go up 2.5 from here. And 2.5 from here is what? 72 inches. That's one standard deviation up. And then I'll go another one, another 2.5, 74.5. I'm just using this 2.5 here. And then I'll use another 2.5 to get finally 77 inches. Hopefully that is right. Yeah, I think that's right. Now we're going to go the other direction. Subtract 2.5. This is 67 inches. This is 64.5 inches. And then finally this is 62 inches. Okay, that's my normal distribution. So what this means is, I'll put the percentages in here again. This is 13.5, and this is 2.35, and finally up here is 0.15 in total. Back there again, that's not one standard deviation, that's all past there. These are percentages of the population that fit in these bands. So let me talk about what this means, and I can ask you how you could ask some specific questions on this. So first of all, it means that 68% of the entire US male population is between 67 and 72 inches. In other words, what is that? 5'7" and 6 foot. That's 2/3 of the population, or sorry, 2/3 of the population within that range, 68%. 95% of the population is between 64.5 and 74.5. And 99.7 is between 62 and 77. 77 is 6'5". I actually have two brothers that are out here in this little curve over here in the 0.15. But okay, so here's some questions you could ask. You could say, in a group of, let's say, I'm just going to use this curve now. Here's some questions. In a group of U.S. males, let's say 2,000, in a group of 2,000 males, how many would you expect to be taller than, how many are taller than 6 feet, which is 72 inches? Okay, so what you do is you say, where's 6 feet on this? It's right here. What percentage of the population is bigger than 6 feet? 13.5 plus 2.35 plus 0.15. Well, that's 2.5. What is that? Should be 16. So that's 16% of the population. Is that? 16% of the 2,000 males should be bigger than 72. 16% times 2,000 is what? 320. So that's how many you expect to be taller than 6 feet. 320. I'm going to calculate it out for some of these in case they get a little more complicated. How many would you expect to be taller in that same group? How much taller would you expect to be taller than 77 inches? So how many bigger than 77 inches, which is 6 foot 5 inches. So pretty damn tall. That number is just 0.15% of the population. So 0.15%. So it's a really tiny number. Times 2,000 is 3. You expect 3 of them out of those 2,000. 3 should be bigger than 3 total. This was 320. So you can see it scales off pretty quickly. 6 footers, there were 320 out of 2,000. 6 foot 5ers, there were only 3. Similarly on the other side, how many people would you expect to have under 62 inches, which is 5'2"? The answer is, again, 3. How many would you expect to be less than 67 inches? 320. You can also do bands of this, for example. Let's say you want to know in the same group of 2,000 males again. How many would be between, I don't know, 64.5 and 67? And 67. You'd expect that to be 13.5%. And of 2,000. So 2,000, actually I shouldn't really need any calculator for this. 13.5%, 0.135 is 270 total in here. So you can distribute the population, the entire US population around this whole group. Notice this adds up to 100%. So it's a probability curve, but it's most often, as I said, used for stats to put statistical data on a curve. But it does tell you by band what percent should be in every group, what percentage of people, what number of people. Okay, that's not so odd. What's really odd to me is that, and it implies something about how biology is set up on Earth, is that if you put this same thing and you put, I don't know, a weight of guinea pigs in the world, it would follow exactly this same characteristic. You put the standard deviations up, you'd get plus or minus 1 would be 68%, plus or minus 2 standard deviations would be 95%, plus or minus 3 would be 99.7. If you put up the heart rate of guppies, it would look like this. So all biological data follows normal curves. Now, we also, as I said, put things like tests on them and things like that, but that's more forced. We actually create tests such that the distribution looks like this. It's a bit more manufactured. Okay, I'm going to do one more. I'm going to put these up here. The only thing I'm going to change, because the percentages don't change, is I'm going to change what I'm measuring. So we're going to do IQ, which is a bit of a human measurement to an extent, although it is trying to measure something that's in nature. IQ of humans. So first of all, you may not know what the average is, or even know what IQ means, but it's supposed to be mental age divided by actual age times 100. So it's centered around 100. So that means the mean is 100. By the way, interestingly, it is about 100 in the US, but there are countries where it's significantly higher. For example, in Singapore, the average, I think, is 108. There are also ones that are lower. But worldwide average is aimed for 100. Okay, standard deviation, you probably don't know this as well, but is roughly 15. So you go up 15, let me write those down. Standard deviation is about 15. So 115, 130, 145, subtract 15, 85, 70, and 55. So there's your IQ distribution. Again, a normal curve, just like the height was before. And again, I can do the same thing. What percent, say in a given population, given pop, do a different number this time, of 1 million people, worldwide, let's say. What percentage have an IQ, or not what percentage, but what number, have an IQ between 85 and 115? Okay, there's the 85, there's 115. The answer is 68% times 1 million, which I have no, so I picked this nice round number. I don't use the calculator for that. It's 680,000. So 680,000 out of a million people would have between 85 and 115. If you want someone who's, find out how many people are really smart, say Einstein level, post 145, it'd be 0.15% of a million. And 1% of a million would be 10,000. So this will be, I'm actually just putting just to make sure, but really shouldn't use a calculator for this. The answer is 1,500, a very small number. That same number would be the number of people under 55 IQ, 1,500 per million. I can also find out what percentage is between 55 and 145, and that'll be 99.7. So 55 to 145 would be 99.7% of the population, which would be 997,000. Or I could say what percent of the population has between 115 and 130. And again, that would be 13.5% of a million, which is 135,000, or in this range right here. And there'll be 135,000 over here as well. 680,000 here, 340,000 there. So you just use that same percentage. Again, it's kind of striking, and mathematicians don't talk about it much, but why IQ should be the same distribution curve as weight, as blood pressure, as height, is very unclear, but kind of a cool thing. All right, that's it. I'm now going to give you the homework. This is the last homework of the year. It's homework 25, and it's called normal distributions. All right, thanks. Till next time.